get this thing started. Stop the music. There's Ariel, just as I'm about to begin. Almost sent it in, Ariel. You barely made it. All right, everybody's here. Good afternoon, everyone. Today is going to be a super awesome day. Continuing our race through the SAT geometric stuff. We're in the middle of three-dimensional shapes. We covered surface area yesterday, which means today we get to volume. It's going to be loud. Not actually, different definition of volume. If you're curious, the etymology of volume means to roll. It has to do with a scroll. Okay, back in the day, before books, things were written on scrolls, and so they used the word volume to refer to, as in volumes of an encyclopedia. Maybe you've heard of that. How it became to represent amount of space and loudness, I have no idea. Went from there, but there you go. Origin of the word volume. But before we get to the volume, let's go back to surface area real quick. Yesterday, you completed these exercises from 8.7. Go ahead and take that out. Check your answers here against mine on screen. First three, very straightforward. Apply appropriate formulas. Same with 4. We talked about number 5. Little tricksy, but doable. 6 has this awkward thing here. You can divide it up any way you like. You could go vertical. Oops, I want the whole thing. Make it easy. There we go. Right? You could just like slice this into these guys and find the dimensions of those rectangles, or you could go horizontal like I had before. Right? I would probably have gone horizontal, but doesn't really matter. Just break this up into rectangles. You can find the dimensions of those based on these on the side and add it all up. And then down here, we've got 7 and 8. With 7, once you got your trapezoid formula, you're all set. Cylinder minus subtract the squares, but add the rectangles. Gets you that guy. We talked about that one. Overall, not too bad. Like 8 is about as tricky as it's going to get. If you can do 8, you are all set for an SAT surface area question. Number 9 is a little more interesting. And I like throwing this one in here because it's such a good real-world application. Because I've literally had to do this before. If you're going to build a project, okay, you want to know how much material do you need. That's very reasonable. So we take all the dimensions of our box here. So it's all these funny shaped sides, all the rectangles, except not the top. They told us that one was made out of glass. So all the rest of it is wood. And we got to figure out, okay, how much total square feet of wood do I need so I know how many sheets to go buy from the store. So if you add those all up, you will get a total of 26 square feet. And a single 4x8 sheet is 32 square feet. So you're all set. You can get one sheet. That's really nice. That's very convenient. I wish my projects would work out that way. I've had to actually go back to the drawing board and say, okay, I don't want to buy a whole extra board just so I can make this thing that much wider. So I've gone back and made my project a little bit smaller so that I could fit it all onto one sheet. But that's not the end of it. Just because you have enough board there doesn't mean you can actually get all those shapes from that board. So the last bit is a little bit of a jigsaw puzzle game. You got to say, hey, is there a way I can arrange these size rectangles and trapezoids that will actually fit? Because, okay, maybe there's enough square feet, but if one of your boards is 12 feet long, you can't cut that out of an 4x8, right? It's too big. So yes, you can. Here is one way to do it. There's lots of ways you can fit this on. There's lots of leftovers space here, okay? So this guy could be over there, and you could have your leftover in the middle, or you could have split these up. However, this is just one method that would work. And we've got all the dimensions there. Now, I will add, since we're on the subject, a little practical, real-world advice. If you do something like this, keep in mind that this whole board is 8 feet, and you want a 3-foot, a 3-foot, and a 2-foot long piece. That is not actually possible. Yes, I know, 3 plus 3 plus 2 equals 8. However, what you're forgetting is the thickness of the lines. Your saw, when you go to cut, okay, this is how wood saws work. They literally churn it into sawdust. Your saw blade is that thick. So you're going to lose that 1/8 of an inch on every cut. And so you have to pick one piece to be a little bit smaller, or center it, and 2 of them are a 1/16 of it smaller. But anyways, a perfect 8-foot board will not actually perfectly cut into a 3, a 3, and a 2 because of the thickness of the blade. So real life tip for you there whenever you're doing measurements. Double check and include the thickness of your blade in your layouts here. I've made that mistake before. All right. Anyone have any final questions on yesterday's work? Not seeing anything in the chat. Okay, then let's march forward for today. We're dealing with volume of prisms, cylinders. Those are very much similar, okay? Take the base, multiply by the height. That's it, this whole thing, okay? Which really summarizes, go back to this guy, right? We had all of the formulas here. So any prism doesn't just have to be perfectly rectangular box. Think of the length, width, and you've got the hidden ones back there. This is your base. Length times width is the base, and you just multiply that by the height. Okay? A cylinder is really a prism with a circular base, right? So that will save you a lot of time right there. Find the base, multiply by the height that is the length of those rectangles connecting them. And that'll take you through pretty much all of these, no problem. Then you get to the next page. Volume of pyramids and cones. Similar, but not exactly the same. Notice in the formulas there, we're going to skip spheres. We'll come back to spheres tomorrow. That we still have the same concept, length, width. Hey, length times width is the area of my base, except now we've got to introduce this fraction 1/3, because I don't have all of the space up here. We've got to, we've taken off some chunks of it. Okay? How exactly it ends up being 1/3 of the space, that's a derivation for another day. Keep that in mind. So when you get to something that's not a square base, figure out how you find the area of the square base, and then you're still just multiplying by height, and then put on a 1/3 for the pyramid and cone. Leave that off for prisms and cylinders. That'll take you through the rest of these questions. I do want to draw your attention, though, to number 2, the hexagonal pyramid, and number 3, the hexagonal prism. Because while all of these are very much plug and chug, what shape is it? Use the formula, put in your numbers, crunch away. You got to make sure you have the right numbers. So in this case, my base is a hexagon, and my height here connects the two would be 10, but I only have the side length of my hexagon. The area for hexagon, in this case 6, would be, we said yesterday, that's 1/2 perimeter times the apothem. Okay, perimeter I got. That's 4 times 6. I've got that. Where's the apothem? They didn't give you an apothem. You can't answer this. You cannot currently, with your current set of tools, answer this question without the given apothem. So this is not doable for us right now. We're going to have to save this for later. Okay? That's the official answer for number 3 right now. Save it for later. Because next week, we get to the special triangles, and that will give us a secret technique for calculating what the apothem will be for this regular hexagon. It'll only work on certain figures, but those certain special figures are so common, they're totally worth analyzing. It's going to be great. Right? So if you see regular hexagon with no apothem given, think, oh shoot, I can't do this yet. Skip that one. We'll come back to those at a later time. Okay? Other than that guy, does anyone have any questions on volume? No? Pretty straightforward questions today. Even the ones at the bottom of the page, right? They're usually the trickiest ones. This is not that bad. It's again, more rectangular shapes there. And I really like the last set, the 7 through 9. You are going to still find the volume of each thing. But then each pair here, they want you to compare them, which is really easy to do. You find the numbers and you say which number is bigger. But I want you to think about these things and compare in your mind and get an understanding for why one of them is bigger than the other. Okay? This is a cylinder with yay dimensions. This is a cone, but it's got much bigger dimensions. It's a much taller cone, right? Which one is actually going to be bigger? Or even better, I really like number 9 down here. Which is more? Do you take 3 small cones or do you take 1 big cone? And this might be like a good question at the ice cream store. Which one gives you more ice cream in the end? Or if we were to do like area, we'll probably go back and do a word problem like this sometime next semester, right? Which option gives you actually more pizza per square inch of pizza? Is it you get 2 small pizzas or 1 large pizza? Right? Everybody wants to know what's the best, most pizza for the buck. And this is the kind of thing, the comparison and having an understanding of how much bigger does the dimension have to be that it overpowers just having more of them. Okay? I really like that idea. Also, if you've ever seen, now I'm thinking of it, there's this great developmental understanding that people's brains go through, the concept of volume and understanding consistency of volume. Okay? That I can take an amount of water in one container and I can pour it into another container and it's still the same amount of water. Because it's really funny, if you take 2 different size glasses, get a nice short, fat glass and a tall, skinny glass, and you take the water in one glass and you pour it into the other glass. So the water level is totally unequal, right? But this one is lower, but it was much wider, see? So the volumes are the same, and we understand that now. But a 4-year-old kid doesn't get that. They think the one that's taller is going to have more every time. So if you have different size glasses and young siblings at home, give that a test. Okay, see if they can figure out which one has more, if any. It usually has the same. But it's that idea, right? Tricking your brain into thinking something has more just because there's more of them. Anyways, I've rambled on long enough. Nobody's popping up questions in chat, so I will stop and leave you with the rest of the period. Many minutes. That's 30 of them. Okay, 30 minutes to work. Have at it. Let me know if you have any questions or get stuck at any point.